Hello, everyone. This is Labor Day edition, part three or part C for chapter 3. Just chillaxing after a nice long weekend. So we'll get right into it. This is all about the patterns of ionization energy and how you can determine or why the different ionization energies change or fluctuate. All right. So you've seen this graph. You made it. There's a few things that are obscure. And the main ones are the dip between group 2 and group 3, in this case beryllium and boron, and the dip between group 5 and group 6, in this specific instance nitrogen and oxygen. So this is what we're going to talk about, why these dip, and the reason it will apply to no matter what elements you're talking about between 2 and 3 and 5 and 6. Okay. So we're going to look at that. So generally speaking, a general rule is as you go across the periodic table, ionization energies increase. Yes, we talked about dips. And then as you go up the periodic table, ionization energy increases. So helium, first ionization energy, should be the highest of every element. Which makes sense because as you go down, they get further away. So the further the distance something is, it's going to take less energy to break that electron away. Okay. So patterns across a period, ionization increases generally, and that's because of the protons. You're within the same shell energy level. Therefore, the size is not really changing. So that means as you increase the number of protons, the attractive force between the protons and the outer electrons is stronger. So more protons, more electrons, greater attraction requires more ionization energy. So some key terms that you want to use in your answering. The nuclear charge, that's the nucleus, increases with the same energy level, so the same size. The distance between the nucleus and the outer electron is approximately the same because you're not changing energy levels, so there's really no change in the distance between the outer electrons and the nucleus. Let me change this. All right. Shielding by the inner electrons are the same, so there's really no shielding of the outside electrons. So you can see here between fluorine and carbon, same energy level. So the shielding between these two electrons is the same, the inner electrons, between fluorine and carbon. So the shielding has no effect on it. So really what you're looking at is the more protons, more nuclear charge is going to have a stronger, greater attraction. With no shielding, and the distance is approximately the same. Okay. So now what about helium to lithium, the big drop? This one we talked about earlier, but as you go from helium to lithium, you can see it's going from a first energy level to a second energy level. So why does it decrease so dramatically? So you can see here neon and sodium. Neon is in 2 energy levels where sodium is in 3 energy levels. So you can see the distance is greater and greater. There's more shielding. And here's some key terms you want to use in your writing. So there is a decrease in activation energy, or ionization energy, sorry. There's less force holding on to the outer electron. Larger radius means less attraction, so less energy is needed. So it's bigger atom. The distance between the nucleus and the outer electron increases, and therefore shielding by the inner electrons increases. So there's now shielding in sodium of the second energy level. There's a shield kind of blocking the energy to get that outer electron, where in neon there's no energy level, so there's no shielding. There's less shielding compared to sodium. And distance and shielding outweigh the increase in the proton charge. So there's a lot more going on to allow less energy to pull that electron than just a proton increase. All right, now the big questions. So beryllium and boron, group 2 and group 3, and neon and oxygen, group 5 and group 6, or 15 and 16. Okay, so that's what we're going to look at here. So from part B in chapter 3, we talked about the subshells and the orbitals, and this is where that comes in play. And then we talked about orbital boxes and electron movement, and that's where nitrogen and oxygen are going to come in play. Okay, so we're going to see why the dip between the two. All right, so look at beryllium and boron. The configuration for beryllium is 1s2, 2s2, 4 electrons, where boron has 1s2, 2s2, and a 2p1. So right there's a big difference. One has a p orbital, where beryllium has just an s orbital. Okay, so that's going to be the big difference. You can see here, further from the nucleus, the 2p has less increasing, or has more energy, takes more energy. There's a shielding effect occurring because of the 2s, and the 2p is further away from the nucleus. Okay, so there's a slight decrease in ionization energy between 2 and 3. You add that 2p subshell, it's further away, okay, from the nucleus, so it needs less energy to remove. The distance between the nucleus and outer electron increases, so the further the distance, less energy is needed. And therefore, if there's another subshell, there's going to be increased shielding. So the 2s is shielding the 2s is shielding the nucleus, so that 2p is easier to remove. So again, 1 and 2, the distance and the shielding outweigh the increase in the proton charge. So that allows less energy to remove that electron. So you're looking at the distance and shielding. That's why there's a dip. Okay, let's look at nitrogen and oxygen. So this goes back to filling in the shells, filling in the orbitals with the box method. So 1s gets filled, 2s gets filled, 2p all get filled, or I mean all have one electron. Where in oxygen, same 2s, 1s, same as nitrogen, adds one more electron. That one more electron is going to be in the opposite spin of the first orbital. You call it X, Y, or Z, doesn't matter, but it has 2 in one of the orbitals, where nitrogen only has 1 in each of the orbitals. Okay, so now spin plays a role. So they're both negative, so they're both going in opposite direction, one going up, one going down, blah, 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 like that. So if they're opposite attracts, that means they are repelling each other. Okay, so that's a big key term, repulsion. Okay, so electron removed from the unpaired orbital takes a little more energy, but here, if you have repulsion, they're paired up, so it takes less energy to remove if they're repelling each other. Okay, it's kind of like two siblings who are fighting. You want to put them in opposite rooms to cool off, so they're easier to remove when they're fighting like that, because they are going ah. Okay, so the extra repulsion being paired with electrons mean for the ionization energy is that it's going to decrease. There's a little less energy needed to remove that electron since they are repelling each other. Okay, so between 5 and 6, this is nitrogen and oxygen group. There's a slight decrease, there's a dip between 5 and 6. 1, spin repulsion. So repulsion means they're going to be pushing away from each other, so it's easier to remove that electron. Okay, so less energy is needed. That's why there's a dip in ionization energy. So the key aspect is this repulsion. It takes more energy to remove a single electron from a orbital, whereas when they pair up, this only happens with the oxygen group, it's easier to remove. All right, period 3 follows the same pattern, so it doesn't matter if you're talking about phosphorus and sulfur or magnesium and aluminum, it's the same aspect. The D block kind of disrupts the pattern, so we're not going to get into too much with the other periods, 4, 5, and 6, but knowing that for the D block starts being introduced, it's going to disrupt the pattern. All right, patterns going down a group. This one's pretty easy. Obviously, the ionization energy decreases. You're adding more shells, so that means the distance from the outer electron and the proton is increasing. So anytime you add shells or adding distance, you have shielding. So again, key terms, shielding increases and the distance increases, okay, from the more energy levels, shells. And again, those outweigh the increase in the protons, so the charge has no really effect on it. All right, so here's some questions from the checkup. Explain these ones you want to answer. You don't have to, there's no homework in this section, but you need to explain the pattern of ionization energies. So from sodium to silicon, there's an increase in nuclear charge in the same period. So the radius is approximately the same. Therefore, no shielding. Therefore, you need more energy to remove the electron. Explain why aluminum has a lower ionization than magnesium. Aluminum's in group 3, magnesium's in group 2. So that's where you have the distance. So the p orbital is further away, causing shielding, and that outweigh the increase in proton charge. You need to explain why fluorine has a higher ionization energy than iodine. So fluorine is in the top of the noble gases. The halogens, and then iodine's way down. So iodine has more shells. Therefore, there's more shells. You have increased distance and more shielding. Okay. So these 3 explanations should be easily explained. Very common questions you will see. All right, so the concepts for chapter 3 is kind of an overview, very important. You need to be able to write the electron configurations of elements and ions. So for example, sodium is 1s2, 2s2, 2p3, 2p6, 3s1. Has 11 electrons. Okay. Fluorine ion gains an electron, so it goes from 9 to 10. It goes to noble gas configuration, which is neon, and neon is 1s2, 2s2, 2p6. You need to determine the group, the column the element belongs to by their large jump in ionization energies. So again, this is part A in chapter 3. So you're looking for big jumps. So here is an example. You look across, the biggest jump is, looks like 6 to 7. Okay, you're increasing about 2,000, 2,000, 3,000, no, 2,000, 4,000, 2,000, and then there's a big jump of almost over 50,000. So 6 and 7. So that means the 6 electrons were removed, so that means it had to be group 6. So you can see the big jump between 6 and 7. That means it has to belong to group 6, which is oxygen group. So it'd be oxygen, sulfur, any of those. You need to be able to draw the electrons using the box orbitals. So you have to visualize how the electrons are located in each subshell and then each orbital. So for example, nitrogen has 1s filled, 2s filled, but then 3 electrons in the 2p, all going in the same direction. Okay. You need to know the ionization trends, so what we just talked about. So why does ionization energy generally increase as you go across the period? because you're increasing charge without increasing the size. Why does ionization energy decreases as you go down? Increasing shells. So as you get more and more shells, there's more shielding. The distance is further away from the nucleus, so it takes less energy. The dip between group 2 and group 3, again, that deals with the distance and shielding. So the p orbital is further away from the nucleus, causing more shielding. Dip between 5 and 6, that's nitrogen oxygen group, that is repulsion. Okay, when you look in the box orbitals, the oxygen has a pair of electrons that are repelling each other, so it's easy to remove. And ionization energy decrease from group A to the next period, to group 1. So it's going to the next energy level. So again, increasing energy shells is going to cause more shielding and more distance, which means less ionization energy. Okay, so these are all common questions that you could be seeing on an ACE paper 2. So you need to have the right terms and using them properly for each of these trends. All right. That's it for chapter 3. So you got a little bit of ionization energy trends and then a review of all chapter 3 in here. So if you have any questions, let me know, and talk to you soon.